So the tangent function is quite different from our sine and cosine function. It's still periodic because it does repeat itself, but it has a very different shape. In fact, we should remember that tan x is the same as sine x divided by cos x. And one thing we learned in our first unit is that we can't divide by 0. So every time cos x is equal to 0, we have the function is undefined, we have an asymptote. And so we have asymptotes for every length of pi on 2. So we have pi on 2, we have pi, we have an asymptote at 3 pi on 2, and an asymptote at 2 pi. So they're repeating itself for pi on 2 plus pi units. So that's the basic tan of x function, and it's asymptotic, which means it's going down to infinity and up to infinity up here for those values. And it gets affected the same way as the sine and cosine function do, that the amplitude out the front is going to stretch it this way. Okay, so it's going to stretch it further. The value of b is going to tell you, tan's a little bit different. The value of b tells you how many wavelengths there are in pi. Okay, not 2 pi. Tan has a period of pi. That's how it's different. And the wavelength formula for tan then is not 2 pi divided by b, but pi divided by b. Okay? C and D, we can both move it sideways and move it up and down, so they both have the same effect as well. So the first one says, sketch the graph of tan of x plus pi on 2. So let's talk about this. If we have tan of x plus pi on 2, what it's going to do is it's going to pick the function up and move a pi on 2 units to the left. So what it means is that this point moves pi on 2 units to the left. This point here moves pi on 2 units to the left. All of the asymptotes move pi on 2 units to the left. So what it would look like, okay, we can think of this asymptote is at minus pi on 2 at the moment. If we move a further pi on 2 to the left, it's going to be minus pi on 2, take pi on 2, it's going to be at minus pi for the first asymptote. Okay, we've moved a further pi on 2 units to the left. This asymptote here is normally at pi on 2. If we take away pi on 2, we're moving a pi on 2 units to the left. That's going to be where the second asymptote is, at pi on 2. The root is normally at 0. Okay, the root, the solution there is normally at 0. It's moved pi on 2 units to the left, so that now goes here. And the function is going to look like this. All right? And it's going to repeat itself. Okay, we only really need to sketch one interval of it, one wavelength. But it is going to repeat itself here with asymptotes pi units apart. Sorry, that's not pi on 2, that's at 0. It has moved pi on 2 units to the left. Okay, good. So that's part A. Let's have a look at part B. Determine the period of y equals tan 5x. Okay, so if we have tan 5x, in this case the value of b is 5. So the wavelength then, the period, is going to be pi on 5. We have one wavelength in pi on 5 units. That's going to be our answer to B. Now definitely for this one we can use our calculators to help us. Our calculators can be a little bit funny with the asymptotes. So with our V window, just make sure you're not zoomed too far out for the y values. I recommend going from probably minus 3 to positive 3 for y. Okay? That's going to help you see the function pretty clearly when you're using your calculator. Now this is a short exercise, which means we should be able to dedicate some time to our folio this lesson. Remember, we don't have a lesson on Thursday because we've got those student-free days and the draft is due Friday. All right, so up to you how you